So we talked about determining empirical and molecular formulas yesterday, and we got to do a couple example problems where we found the empirical formula of a compound, right? That's the lowest whole number ratio between the atoms in a compound. So let's do one more example like we did yesterday together. We'll start with number 4. So it tells us we have an unknown iron oxide compound. So it's a compound that just has iron and oxygen, and it gives us the percent iron. We can do our first step pretty easily, go percent to mass. And so we're pretending we have 100 grams, which would make this 69.94 grams of iron. But we do have a small problem. We don't have the percent of oxygen, but we can find that pretty easily because we know the percents have to add up to 100. Pause the video for a second and find the percent of oxygen. Hopefully you found the percent of oxygen to be 30.06%, and we can translate this into grams the same way, a nice easy step. Now we're going to do step 2, and we're going to convert the masses we have to moles. Just a quick mole conversion. We're going to put the molar mass on the bottom and 1 mole on the top for each of them. Pause the video and do that. Now that we have our moles of our substance, we're going to divide by the smaller number of moles. So we'll divide them both by 1.2523 and get an answer here. Round to a whole number if it's really close, but if it's not, keep maybe 1 or 2 places after the decimal. So iron came out to be 1, but oxygen isn't really close to 1, it's not really close to 2. It's pretty much 1.5. So here's where we have to do our last step. Our chemical formula this way would read Fe1O1.5, but we know that's not okay to write. It has to be a whole number ratio. So the easiest way to do this is to double both of them, and then we get Fe with a subscript 2 and O with a subscript 3. And that's the same ratio as a 1 to 1.5 ratio, but now it's a whole number. And that's our chemical formula, and that's how you do the last step, the multiply till whole step. Am I driving you nuts? That gives us a total of 29.07 grams. That's how much 1 mole of C2H5 would weigh. But we know that's the lowest whole number ratio, and it tells us that the molecule actually is supposed to weigh 290 grams. So that's a whole lot more. Now, we also know that this chemical formula, C2H5, is the same ratio of atoms as in the compound. So for example, we could double all of them, and then we could get C4H10. That's the same ratio. Or we could triple all of them, and we could get C6H15. Or we could quadruple it, right? Multiply both those subscripts by 4 and get C8H20. And what we could do is we could double check and see what all these molar masses are. We could add it all up. We could do 4 carbons plus 10 hydrogens, right? And then we could do 6 carbons plus 15 hydrogens. But that would really take a long time. Maybe take a second and see if you can figure out an easier way to do it. Pause the video now and see if you have an idea. Maybe you thought of doing the division this way. Take your molecular mass and divide it by your empirical formula mass, and you'll find out how many times the empirical formula fits into the molecular formula. So you're taking the big number and dividing it by the small number. And in this case, you'll get 10. Maybe you also just looked at these two numbers and noticed that if you multiplied it by 10, you pretty much got the molecular mass. that will always be true, and it's always going to be like a nice easy number, like 2, 3, 4, or 10. What that means is that this was actually supposed to be times 10, so that gives us C20H50, and that is our molecular formula. So our empirical formula, the smallest whole number ratio was 2 to 5, but the actual molecule, when it's found in nature, has 20 carbons and 50 hydrogens. That's a big molecule, but sometimes we have big molecules. Okay, last problem. Let's put all our skills together. So we're given a compound that has 0.44 grams of hydrogen and 6.92 grams of oxygen. Our first step is always to take the percent and make it into a mass. But lucky us, they actually already gave us masses. If you're already given masses, you get to skip that first step. Okay, so we set our problem up and we kind of went percent to mass. We already had mass, great. That makes it a little bit easier. Now we're gonna go mass to moles. Pause the video and go mass to moles, or maybe even go the whole way through and get your empirical formula. Okay, we've got our number of moles. Now we're gonna divide by small. So we pretty much get a 1-to-1 ratio. Neither of them are like 0.5. So we can say that our empirical formula is a 1-to-1 ratio, H subscript 1, O subscript 1. Now what we're going to do is we're going to figure out the molecular formula. So it's going to be some multiple of this. We just don't know what it is. The first step in doing that is to calculate the mass of this, which is a pretty easy one. So we're going to add up hydrogen and oxygen, the masses of both from the periodic table, and that gives us 17.01 grams. And then we already have the mass of the empirical formula. Now that's our 17.01, and the 34 grams per mole, that's the mass of our molecular formula. So we're going to figure out how many times that'll fit into the 34 grams per mole. And we do that by dividing it by 17.01 grams. And that tells us it's going to fit in 2 times. So we're going to have to take this formula and multiply it by 2, which makes it H2O2, which is hydrogen peroxide. And if you want, you can double check. You can say 2 times 1.01 plus 2 times 16, and that's going to give you pretty darn close to 34 grams per mole. At this point, you should be able to finish the active chem problems on empirical and molecular formulas.